In this video, we are going to discuss another type of graphs. Then we will describe the concept of graph coloring. Sometimes a graph has the property that its vertex set can be divided into two disjoint subsets, such that each edge connects a vertex in one of these subsets to a vertex in the other subset. For example, consider the graph representing marriages between men and women in a village, where each person is represented by a vertex and a marriage is represented by an edge. In this graph, each edge connects a vertex in the subset of vertices representing males and a vertex in the subset of vertices representing females. This leads us to the following definition. A simple graph G is called bipartite if its vertex set V can be partitioned into two disjoint sets V1 and V2 such that every edge in the graph connects a vertex in V1 and a vertex in V2, so that no edge in G connects either two vertices in V1 or two vertices in V2. When this condition holds, we call the pair V1, V2 by a partition of the vertex set V of G. So let us take an example. C6 is a bipartite as shown in figure 1, because its vertex set can be partitioned into the two sets V1, which equal V1, V3, V5, and V2, which equal to V2, V4, V6, and every edge of C6 connects a vertex in V1 and a vertex in V2. Another example of bipartite graph, consider the graph K3 shown in figure 2. K3 is not a bipartite. To verify this, note that if we divided the vertex set of K3 into two disjoint sets, one of the two sets must contain two vertices. If the graph were bipartite, these two vertices should not be connected by an edge. But in K3, each vertex is connected to every other vertex by an edge. Let us take one more example. Are the graphs G and H displayed in figure 3 bipartite? Graph G is bipartite because its vertex set is the union of two disjoint sets, which are A, B, and D, and the second set C, E, F, and G. And each edge connects a vertex in one of these subsets to a vertex in the other subset. Note that for G to be bipartite, it is not necessarily that every vertex in A, B, D be adjacent to every vertex in C, E, F, and G. For instance, B and G are not adjacent. Now, graph H is not a bipartite because its vertex set cannot be partitioned into two subsets, so the edges do not connect two vertices from the same subset. The viewer should verify this by considering the vertices A, B, and F. So the following theorem provides a useful criteria for determining whether a graph is bipartite. A simple graph is bipartite if and only if it is possible to assign one of two different colors to each vertex of the graph so that no two adjacent vertices are assigned the same color. Now we will use the theorem to determine whether the graphs in above example are bipartite. We first consider the graph G. We will try to assign one of two colors, say red and blue, to each vertex in G so that no edge in G connects a red vertex and a blue vertex. Without loss of generality, we begin by assigning red to A. Then we must assign blue to C, E, F, and G, because each of these vertices is adjacent to A. To avoid having an edge with two blue endpoints, we must assign red to all the vertices adjacent to either C, E, F, or G. This means that we must assign red to both B and D, and means that A must be assigned red which it already has been. We have now assigned colors to all vertices with A, B, and D red and the vertices C, E, F, and G blue. Checking all edges, we see that every edge connects a red vertex and a blue vertex. So, by the above theorem, the graph G is bipartite. Next, we will try to assign either red or blue to each vertex in graph H, so that no edge in H connect a red vertex and a blue vertex. Without loss of generality, we will assign red to A. Then, we must assign blue to B, E, and F. Because each is adjacent to A, but this is not possible because E and F are adjacent, so both cannot be assigned blue. This argument shows that we cannot assign one of two colors to each of the vertices of H so that no adjacent vertices are assigned the same color. It follows by the theorem that H is not a bipartite graph. A complete bipartite graph K of M and N is a graph that has its vertex set partitioned into two subsets of M and N vertices, respectively, with an edge between two vertices. If and only if one vertex is in the first subset and the other vertex is in the second subset. The complete bipartite graphs K2 and 3, K3 and 3, and K3 and 5, and finally K of 2 and 6 are displayed in figure 6. Bipartite graph can be used to model many types of applications that involving matching the elements of one set to elements of another, as the following example illustrates. Suppose that there are M employees in a group and N different jobs that need to be done, where M is greater or equal N. Each employee is trained to do one or more of these N jobs. We would like to assign an employee to each job. To help with this task, we can use a graph to model employee capabilities. We represent each employee by a vertex and each job by a vertex. For each employee, we include an edge from that employee to all jobs that the employee has been trained to do. Note that the vertex set of this graph can be partitioned into two disjoint sets, the set of employees and the set of jobs, and each edge connects an employee to a job. So this graph is bipartite, where the bipartition is E and J, where E is the set of employees and J is the set of jobs. We now consider two different scenarios. We model these employee capabilities using the bipartite graph in figure 5a, and second, we suppose that a group has a second group also has 4 employees, so we model these employees capability using the bipartite graph shown in figure 5b. Another example of the application of bipartite graphs can be taken about the marriages on an island. Suppose that there are M men and N women in Iceland. Each person has a list of members of the opposite gender acceptable as a spouse. We construct a bipartite graph G equal the subset V1 and V2, where V1 is the set of men and V2 is the set of women, so that there is an edge between a man and a woman if they find each other acceptable as a spouse. A matching in this graph consists of a set of edges where each pair of endpoints of an edge is a husband-wife pair. A maximum matching is the largest possible set of married couples, and a complete matching of V1 is a set of married couples where every man is married but possibly not all women.